Ladies and gentlemen, today we're going to be moving on to Chapter 3, and Chapter 3 is about exponential and logarithmic functions, so two other kinds of functions. We've done linear, quadratic, polynomial, rational. So these are two new types of functions, and today we're just going to be talking about exponential functions and their graphs to start off with. So first of all, let's look at the parent exponential function. So right here, your parent exponential function is f of x equals a to the x, where a can be any real number. Okay, so you can make any real number right in there, and that'll work. So here's an example, just a really simple one. F of x equals 2 to the x. So let's look at the way the graph of this thing looks if we plug in some points. So if I plug in 0, well, 2 raised to the 0 is 1. Anything to the 0 is 1. So when I plug in 0, I get 1. So we put a point at 0, 1. When I plug in 1, 2 to the first is 2. So go over 1 up 2. When I plug in 2, 2 squared is 4. So I plug in 2, 4. When I plug in 3, 2 to the third is 8. So over here it's 3. I'm going to go up to 8. All right, and then if you plug in any negatives, well, 2 to a negative 1. All right, anytime you raise something to a negative, okay, what you need to do is move it to the bottom of a fraction and just leave a 1 on top. Okay, so 1 over 2 to the first is the same thing as 2 to the negative 1, which is just 1/2. So when I plug in negative 1, I get a half. When I plug in negative 2, of course, it would be 1 over 2 squared, so that would be a fourth. And then you get the idea, an eighth. And it's going to get closer and closer to this line, but it's never going to touch it, right? So we have an asymptote on exponential functions. Now, it's a little bit different than rational. We don't have two asymptotes, like a vertical and a horizontal. We just have a horizontal asymptote when we have exponential functions. So we're going to have a horizontal asymptote at 0 for that function. The graph's never going to get to 0 because you can't raise 2 to anything and get 0. So that's the basic function for 2 to the x. Notice it grows quicker over time. You'll hear people talk about things growing exponentially or things growing geometrically. This is what they're talking about, how as it grows, it starts growing faster and faster and faster. And eventually you'll get, you plug in 4, well, it's 4 and 6, the y coordinate's 16. And then 5, the y coordinate's 32. So it gets bigger, faster and faster and faster. Okay, so let's look at just some shifts on this, just a reminder of some shifts. If we had f of x equals 2 to the x, and you added a number out here. All right, well, what that's going to do is it's going to take the function that we just looked at. Let's see if I can group this stuff. And we'll copy it and paste. All right, so now we've got another one. Oh, I'm moving the wrong thing now. Let's move that back. There we go. Okay, so right here would be the function. Well, the plus 2, all it's going to do is make the function move up 2, right? So you just move it up to there. Everything else will look the same. So your asymptote moves up, all the points move up, right? Of course, if you subtracted 2, if you had a minus 2 right here, that's just going to make the graph shift down 2. Oh, thought I had them all grouped together. Let's get those things grouped together real quick. Oh. There we go. So if it's 2x minus 2, then you're going to start right here, but you're going to shift down 1. You're going to shift everything down once, twice, right? So your asymptote would now be down at negative 2. All the points shift down 2 also. All right. Of course, if you add or subtract a number on the inside, which in this situation, the inside is the exponent. So if I said 2 times raised to the x minus 3, well, that's inside. That moves things left and right. So that's going to move your graph 3 spots to the right. So the entire graph right here, everything's just going to move 3 spots to the right. Of course, it's a little tough to do. Everything, I'll just limit 1, 2, 3. You get the idea. So that's where your points would be. Going on, the asymptote would stay in the same spot, but your line would all shift over. Okay, of course, if it was x plus 3, then you're going to move it left 1, 2, 3. Asymptote would stay in the same spot, but the points would all shift. Okay, so those are just your basics. Now, if you have a negative out front, so let's say it was like this, negative 2x, then that's going to flip it vertically. Okay, so then you're going to have this situation right here. So we can flip this. So it'll look like that now. Okay, and it's going to go through -1, right? So it's just mirrors, just going to mirror across the x-axis if you put a negative on the outside. All right, so that would be your function for a negative on the outside. If you put a negative on the inside, so you put a negative up here with the x as opposed to out front, 2 raised to the negative x, then that's going to flip it across the y-axis. So that would flip it to look like this right here. Okay, so those are the shifts that you're going to see most often on these, is flip vertically, flip horizontally, or just shifting it up, down, left, and right. Okay, but that's the basic function for 2. Of course, as this number gets bigger, if it's 3 or 4 or 5, it can be anything, right? Then that's going to change the way this function looks. It's going to stretch it up a little bit taller. So that's something that you'll see, just when you have different bases. But we just need to remember the transformations and understand how they're going to work with an exponential function. All right, let's go on. Talk about something called the natural base. So the natural base, we use the letter E to represent the natural base. And here's the definition, essentially, of the natural base. Okay, so the natural base, E, is what you get when you evaluate this function right here, 1 plus 1 over x raised to the x, as x approaches infinity. So as x gets bigger and bigger and bigger and bigger, you're getting closer and closer to the actual value of E. All right, so now let's look at this on a calculator. I'm going to graph this. 1 plus 1 over x. I'm going to raise it to the x. All right, so let's look at this graph right here. I think I typed it in wrong. Let me check it. No, that's right. Okay, so yeah, we're just looking at the positive side. So I'm going to change the window to go from 0 and 0. So just look at the positive side. Okay, so you can see how it flattens out. It's getting closer and closer to some value in here, right? So it's never going to get there. It's an asymptote, but it's getting closer and closer to something. Because we have an asymptote, obviously, and you can use the E button right here to see what that value is. So see right here, there's a blue E right here on the calculator above your divide button. All right, so we hit second E and just type that in, and it'll show you a line right across here. So see, that's the line that it's approaching, right? And we can see what that value is if you go to the table. That value is about 2.7183. So you can see here's your line, and you can see that number is getting closer and closer to E, which is 2.7183. The bigger x gets, the closer we're getting to E. So that's just a way to know what E is. So E is just a random number. It's kind of like pi, right? If you just plug in E to the calculator and hit enter, there's some random decimal, right? Just like pi is 3.14 blah blah blah. E is something random, okay? But it's a very valuable thing to use as a base in a function because it comes up sometimes in real life situations and is useful in real life situations. This little part right here is something that mathematically comes up a lot in the natural world. So that's what we call E, the natural base. So right here you can see E being used as a natural base. F of x equals E raised to the x. And here's what the graph looks like on the calculator when you use E as a natural base. So if we did E raised to the x, you can see this graph right here on the calculator. Looks like another exponential function, but this is where your base, right, is that instead of 2 like we used on this last slide right here, we use 2 as the base. Now the base is E, which as we remember is 2.7183, blah, 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 blah. So the function looks pretty similar to this one, right? But it's going to be a little bit steeper than this one because E is really 2.7 something instead of just 2. So that's just a basic idea of what E is. Okay, it's again kind of like pi, just a random decimal that we use in the real world that happens sometimes. Right. So let's look at applications of the natural base. One application is in banking. Right. So if you invest some money in a bank account, and the bank account's going to grow over time, your interest rate's going to make you add on some money to your account. So we use E a lot of times to do that. So a couple different formulas that you need to be aware of right here. Okay, the amount in your account is going to equal P, which represents the principal. The principal is the initial amount you put into your account. Okay, P times 1 plus R over N, where R is your interest rate, raised to the NT. Now, both of those N's represent the number of times that your interest is calculated a year or compounded a year. Sometimes you hear the word compounded. So N is how many times it's compounded or calculated per year. And of course, T is the number of years, the time in years that you leave your money in the bank or leave your money in whatever account it's getting that investment added onto. So that's one formula. Another one that you'll see is this right here called the PERT formula. This one uses E. It's your principal times E raised to the rate, the interest rate times the time. Okay, so the difference in these two is you use the blue formula anytime the interest is compounded, anything but continuously. Okay, so if it's compounded daily or monthly or annually, quarterly, weekly, whatever, anything besides continuously, you're going to use the blue formula. Okay, you use the red formula if it's compounded continuously. All right, so if they just say you compound your interest continuously at this bank or whatever this account is, then you'd use the PERT formula. Anything except continuously, use the blue one. All right, so let's look at some problems right here to practice. So it says a total of $9,000 invested at an annual interest rate of 2.5%. Find the balance in the account for 5 years if it is compounded, and they give you a bunch of these choices: annually, monthly, quarterly, blah, 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 blah. So again, if it's not continuously, we're going to use the blue formula. So let's use the blue formula right here for annually. So P, the amount that's in the account is going to be P, which is the principal, the amount we start off with in the bank, $9,000 is what we put in, times 1 plus R, which is our interest rate. Okay, now when you put in your interest rate, you need to convert it to a decimal. So when we make a percent into a decimal, we've got to move the decimal twice to the left. So it's really 0.025. Okay, plug in for R. Then we put it over N. Remember, N is the number of times you calculated a year. Okay, so if I do it annually, if I do something annually, how many times a year is that? Well, that's just once, right? Like they have that annual, festival or whatever. They do it once a year. So if we just do it once a year, we just put 1 in for N because it's annual. And up here we got N again, so we put 1 times, and then your time, well, it tells us our problem, we're going to put it in for 5 years. Okay, so now you just used your calculator, and you can type this in. Just make sure if it's in parentheses, you put in parentheses. If it's an exponent, you make sure it's in the exponent. 9,000 times 1 plus 0.025 divided by 1, close your parentheses, raised to 1 times 5. Make sure all that 1 times 5 is up in the exponent, and hit enter. And you should get $10,182.67. We're going to round it to the hundreds because we're talking about money. So we're going to round it to the cents. So if you had an account, you put $9,000 in it with a 2.5% interest rate, and it's compounded annually for 5 years. Then after those 5 years, you're going to have $10,182.67 in your account. Let's do it for monthly. So monthly, the only thing that's going to change is N. Okay, we still have the same amount, 9,000 times 1 plus 0.025, same interest rate. But now if we do it monthly, how many times a year do we do it? 12, right? So N is 12, 12 times 5. Okay, so you're going to use the exact same formula, type in everything exactly the same, except now instead of 1, you're going to put 12 in place of N. All right, so we plug those in, everything else is the same, hit enter, and you should get $10,197.01. Not quarterly. So now how many times a year is it? Well, if you do it quarterly, I think 4 quarters in $1, you do it 4 times a year, every 3 months is what quarterly means. They talk about those in the business world a lot, you know, first quarter or second quarter. They're talking about the first 3 months of the year and the second 3 months of the year and all that good stuff. So we plug in 4 in, and we get $10,000, $194.37. All right. Now let's look at daily. So if we do it daily, how many times a year do you do it? Well, it's 365 days in a year. We're assuming it's not a leap year whenever we do this formula. So we're going to plug in 365 for n. Everything else is the same though. So we got 365 times 5 in our exponent, and we're going to divide by 365. And whenever you plug in 365, you should get $10,198.29. Okay, now the last one, continuously. Continuously means you're doing it every second, every day. It's continuously being calculated. All right. Now it's not really secondly, it's continuously. It's even more often than that. It's like you're calculating it down to the infinite time amount that you could possibly use. The smallest time amount you could possibly use is what you're calculating to. So now when you use continuously, right? Continuously, we use the red formula, the PERT formula. Okay, so we're going to use the same principle, the same rate, and the same time, but we're going to plug it in with the E. So A equals P, which is 9,000, times E raised to the R, still make it a decimal, times the time. Okay, so a little bit different whenever you're calculating continuously. So 9,000 times E raised to 0.025 times 5. And whenever you do that, you get $10,198.34 whenever you round it. Okay, so right here you can kind of notice that the most beneficial thing, right, is to have an account that's calculated continuously, because that's where we yield the most money after 5 years. $10,198.34. If we did it daily, right, you get $10,198.29. So you get like 5 cents more. Of course, the more money that's in the bank and different interest rate and stuff can affect how much difference you're going to have between daily and continuously. But as you can see, like you go down to annually, and it's only $10,182.67. So that's like another 15 or 16 bucks to go from annually to continuously. All right, so let's practice. Let you guys try doing some of these with this problem down here. Actually, that's the exact same problem, so let me change it real quick. That's better. So let's do it with this problem right here. You got $15,000 invested at an interest rate of 3.5%, and you want to figure out what's the balance after 10 years if you compound it annually, monthly, quarterly, daily, continuously. All right, so give that a try, and you can check and see how you did. Okay, so here's your answers that you should get for each of these. If you have questions about where they came from, let me know, and I'll come around and help you. But those are the answers for annually, monthly, quarterly, daily, continuously. Again, notice continuously is the one that's going to yield us the most money. Of course, the next most is going to be daily, then monthly, then quarterly, then annually. The more times you calculate it, the bigger N is, the better you're going to do. Continuously is basically if you plug infinity in for N. Okay, so that's why it's always the best. So let's look at some other examples when you use exponential functions besides just with bank accounts. So radioactive decay, something you might talk about in chemistry class or biology. So let Y represent a mass in grams of radioactive strontium whose half-life is 29 years. So radioactive materials, they decay over time, and we talk about their half-life. So that's essentially the amount of time it takes for there to only be half the substance left. So that means for strontium, every 29 years, there's half as much left as what there was 29 years ago. All right, so here's the function that we use for that. All right, then we'll know what's the initial mass if this is our function. So to figure out the initial mass, you would plug in the time as 0, right? So we can do that algebraically, or we can do it on the calculator. Of course, you can see right here, if I plug in 0 for t, well, 0 divided by 29 is 0. So you got 10 times 1/2 raised to the 0. Something raised to the 0 is just 1. So it's really 10 times 1, which is just 10. So that means your initial mass is 10. Okay, you plug in 0, that'll give you your initial amount that you started off with. So we start off with 10 grams of strontium. So we could label it with grams. Sometimes, you know, they like us to do that. So 10 grams is how much you start off with. We want to know how much is present after 80 years. So again, you can plug in 80 for T, just type it straight in the calculator to figure that out. Or another option you have is to graph it. So let's look at how we do it if we graph it instead of doing it algebraically. So let's say I plug in the function. I got my function 10 times 1/2 raised to, and when they use T, we'll just plug in x over 29. Alright, so we graph that. And we can't really see anything, but what we're more interested in is the table. Okay, so let's look at second table, and we can see these values right here. So we're curious about how much is left after 80 years. So when T is 80, or in our calculator we used X, right? So how much is present after 80 years? So we just need to scroll down to 80. Of course, we talked about how you can get it to scroll faster. So maybe if I want to count by tens to scroll faster, I can hit plus 10. And it'll count by tens. I can go down to 80. So 80 years, there's going to be 1.47 or 1.48 grams left. Okay, so you can use your calculator. Of course, you can plug that in. You can just plug in 80 into the calculator and into the formula and do the math, figure out what it would be that way too. All right, so that's how you can figure those out. So go ahead and try the one down here and see if you can figure out these questions right here. So here are the answers for these three questions. 10 grams, the initial amount. 8.86 grams will be left after 2,000 years, and there'll be 2 grams left at 13,270 years. So again, most of this, the easiest way to do it is on the calculator. So to determine the initial quantity, you can plug in 0 for T, or you can just look at the table. So if you look at the table, you see when T is 0 or X is 0, the initial amount is 10. Then to figure out how much is going to be left after 2,000 years, we can scroll down to 2,000, which of course is going to take a while. So if you press plus, right, and then put in 1,000, it'll make you count by thousands. Okay, so now we can count by 1,000. We go down to 2,000 and see, oh, 7.85 grams is what would be left. Hold on a second. Is that right? Did I look at it wrong a minute ago? Oh, I think I looked at 1,000 grams. Yeah, I looked at 1,000 years. Sorry, 2,000 years is going to be 7.85 grams. I looked at this one, wrote 8.86. So this should be 7.85 grams. And after how many years will there be 2 grams left? So we need to figure out in this Y column, when does the Y column get down to 2? So when I scroll down, I see that it's around 2, you know, somewhere right around in here. So I'll go to 13,000, and now let's make it count by hundreds. So count by 100, and now we can see all the hundreds. So 13,100, 13,200. So it looks around 13,300. So let's make it count down even more, 13,300, and let's make it count by tens. So we can see even smaller numbers. Looks like it's 13,270, and we can make it count by ones if we want to see even closer. 13,270, looks like that's when it's exactly 2. So we'd say 13,270 years. Okay, now of course to make it go back to counting by 1 starting at, you know, wherever you want to go to, you got to make it count by, you want to make it count by tens first. So go to 70, make it count by tens. Then you can scroll to where it's at 100, like 200, see? So now when you get to 100, you can make it count by hundreds. This will keep you from messing things up. Now it's counting by 100, so you can get to where it's, you got an even 1,000, 3,000, and make it count by thousands again. And then you can go down to 0 real easy and make it count by ones. You can get back to your normal table. All right, so that's how you can use the calculator to do these. It's pretty simple, just basic calculator work. Let's look now at another type of real-life problem, population growth. So approximate the number of fruit flies in an experiment. Experimental population after T hours is given by this function right here. Want to find the initial amount? Well, we know how to do this. Let's graph it and see what we get. So we do 20. Now we've got E on this one. e raised to 0.03 times t, or x. We can graph it and then look and see where it is. When x is 0, what do we get? So look at your table. When x is 0, your initial map's 20. So we've got 20 fruit flies to start. How large is it after 72 hours? So we would need to scroll down to where t is 72, because t is given in hours. So we would maybe make it count by tens or something, scroll down to 70, and then start making it count by ones again. So 72, you should have about 173 fruit flies after 72 hours. Okay, so your initial is 20. Then you've got 173 after 72 hours. And how long will it take the population of fruit flies to get up to 1,000? So we need to scroll until the Y column gets up to 1,000 and see how many years that takes in the X column. All right, so we can do that. Doing the same thing we did on the last problems. So it's going to get to 1,000 after 131 hours. Okay, so again, that's just scrolling through the calculator, figuring it out the same way we did the last problem. Now we're talking about population. So you guys try this last one right here. Let me know if you have any questions, and I'll come by and help you. So after plugging this function into the calculator, looking at your graph and table, okay, you can scroll down and see that the year when the population is going to exceed 50 million is 2038. So we still got about 20 years, according to this model, for California's population to get up to more than 50 million. Again, that model can change over time, but for all intents and purposes, at this point, it's 2038 when we expect that to happen. The population in 2018, we can get a scroll now to see when x is 18, right? Because remember, in this problem, if x is 15 or t is 15, that corresponds to 2015. So 18 corresponds to 2018. So when we scroll to 18, we see that the population should be about 41,327,000. Be interesting to look it up and see what it actually is. Y'all can do that and see how close our model is to the actual data for this year. But that's it pretty much for exponential functions. Let me know if you have questions. Here's some problems to practice doing some of these things. Let me know if you need help.